So, last class we were talking about moments of inertia and products of inertia. We defined the moments of inertia as Ixx, Iyy, Izz, or some books use a single axis notation Ix, Iy, Iz as integral of each point which you take on the mass. Whichever axis you are taking the moment of inertia about, you take the square of the distance, multiply it by the mass, add it up for all the masses, that gives you the moment of inertia. And then we have the product of inertia, which are something new which was introduced. Ixy was introduced as integral of xy dm, Ixz integral xz dm, Iyz integral yz dm. And together for this, once we have defined this, what I told you was that we can define a matrix which we can call as the inertia matrix, and this we can write it as Ixx, Ixy, Ixz, Iyx, Iyy, Iyz, Izx, Izy, Izz, and this is the inertia matrix. And we can then we know that this is a symmetric matrix. Now, we also call this as the inertia tensor. A second order matrix can also be termed as what is called a second order tensor. Have you heard the term tensor before or not? Probably not. You would have heard the term vector, scalar. Well, tensor is an extension of these concepts. In fact, a scalar is what we can term as a zeroth order tensor. A vector is a first order tensor, something which we write in a 3 by 3 matrix form. This would be a second order tensor, and so on. Now, if we look at mathematical definition of a vector, not the physical one. If I ask anyone who is doing physics what is a vector, the answer will be a quantity which has a magnitude and a direction. If you ask a mathematician what is a vector, how would they define?
A directed line segment.
That is exactly what was the physicist's definition.
Row matrix 1 and 2.
It would be a row matrix with this thing that it transforms according to a certain rule. That when you have a matrix which is there, and if it transforms, if you rotate it, that means if its components are x comma y comma z, now you make new you rotate about the original axis, you have new axis x prime, y prime, z prime. Then the way you find the new components, they are related to the old components through direction cosines, and there is a particular rule which this transformation follows. And what a mathematician will say is, anything, any quantity which follows this transformation rule is a vector. They will not say a directed line segment, which is what a physicist would say. And both the things are important. Now, the reason I am bringing this up here is, at least I will just slightly go into this discourse, that this quantity which we have, which I am saying this is a second order tensor. So, this will also, that means if you have, so let us try to give the physics of this also. That means I have axes x, y, z, and on which I am finding the moment of inertia matrix. Now, I make let me use the red color for this. So, I have on the same origin I have a new set of axes x prime, y prime, z prime, which are obtained by rotation and maybe reflection of the original axis. So, how I obtain x prime, y prime, z prime will be known to me. Okay. And how will I know them? Through direction cosines. Direction cosines of x prime will be what? The cosine of the angle between x prime and x, cosine of the angle between x prime and y, cosine of the angle between x prime and z. They will give me the direction cosines of x prime. Similarly, I will get direction cosines of y prime and direction cosines of z prime. Okay. Now, once we have this, then a second order tensor will be a quantity which will follow a similar rule for transformation. If I know the inertia matrix for x, y, z axis, can I find the inertia matrix for x prime, y prime, z prime? And if that rule is followed, then we say this is a second order tensor from a mathematician's viewpoint. From a physicist's viewpoint, what is a second order tensor? We have two vector quantities and we allow both the vectors to retain their identity. And probably inertia is not the right quantity to start explaining the physical this thing of a second order tensor. A better quantity is stress. How do we define a stress? Force divided by area. Force is a vector, area is also a vector given by its outward normal. Now, if I allow force and area vectors both to be independent, that means force direction could be x, y, z. Similarly, area's direction could also be x, y, z. When I put both of these together, how many possible combinations will I get? 9. Force could be in x, area could be in x. Force could be in x, area could be in y. Force could be in x, area could be in z, and so on. So, totally I will get 9 combinations. And again that becomes what is a second order tensor. So, you have two vector quantities. We will not go in the mathematics of this, how they transform. But similarly here in inertia matrix which we have, we can now, given inertia matrix about x, y, z, I can rotate it, and for different rotations I will get different components of inertia. And we have already in the last class towards the end I told you, if I know the x prime matrix which I told as referred to as k, then I can find I k k if I know I x, I y, I z and other inertia terms. So, a bit of the flavor we have seen. But from here let me now try to come to the concept of principal axis. So, suppose if there is a set of axes where the inertia tensor has the form I rotate, I have infinite combinations about x prime, y prime, z prime in the previous figure. If suppose I am able to get one particular x, y, z where the inertia matrix takes this form, that means all the products of inertia are 0. And maybe what I can do is I can call it as star. Star represents, so that means in the star axis I x star y star is equal to I x star z star is equal to I y star z star is equal to 0. So, about this starred axis I do not have any products of inertia. Then I say if this is the case, then x star y star z star, they are referred to as the principal axes. I did a slightly more simplified form in the last class where I said if Ixy is 0 and Ixz is 0, then x is a principal axis. I am generalizing that now to 3 mutually perpendicular sets where if x star, y star, z star, all their products of inertias are 0 about that, then we have principal axis. Okay. Now, mathematically, how do I find the principal axis? And again, this is something which I will just tell you. We will use some of the properties to show some nice details, but mathematically, the principal axis corresponding to the inertia matrix are what? They are the eigenvectors of the inertia matrix. So, I have the inertia matrix. If I find its eigenvectors, you know how to find eigenvectors. You take a matrix, you first find the eigenvalues corresponding to each eigenvalue, you put a lambda, a v is equal to lambda v. So, you lambda is the eigenvalue, you know a matrix, that is your original matrix. So, you will be able to find the vector v. You take one of its component as 1, take the other two as x, y, and then you will be able to solve for x and y. That is how you find the eigenvectors. It is very simple if you have to carry out the mathematical exercise. So, the eigenvectors of the inertia matrix, these are the principal axis. Okay. Now, this I have stated without proving. I am not proving the proof, and I will not prove it. I will not go into proof of this. I will just state this, that eigenvectors of the inertia matrix are the principal axis. Okay. And the eigenvalues, these are so if I call x star, y star, z star, the corresponding eigenvalues will be the moments of inertia corresponding to that axis. So, if there is an axis, one of the eigenvectors is you choose it, you can choose your x star, y star, z star along the 3 eigenvectors. Now, the question you will ask is, how do I know they are mutually perpendicular and do they exist? And again, for that I will just refer to mathematics. I will not prove this, but it can be shown if a matrix is symmetric, then its eigenvalues are real, and the eigenvalues are real and the eigenvectors are real. So, for every symmetric matrix you should be able to find set of eigenvalues which will then represent the eigenvectors which will represent the principal axis. So, this is the mathematical way of finding the principal axis, but we will not look at that. We will not ask you to do this. In this course, we will not ask you to find principal axis using this. Pardon? No, yeah, I will come to that also. There can be more than one principal axis. Now, what will happen is, so suppose you convert things, you find the eigenvectors. If the eigenvectors, in fact, this will lead to some very interesting things which I will show. If the eigenvectors are I11, I22, I33, or sorry, eigenvalues are I11, I22, 33. Now, vector V1, this will correspond to, let us say, x star, V2 will correspond to y star, and vector V3 will correspond to z star. These are the eigenvectors. Now, a very interesting point has been asked about, can there be more than one principal axis? I think that is what you were basically asking, and the answer is yes. Now, what will happen is, if, and again I will just state this without proving, if I11, I22 and I33 all are distinct, we have different eigenvalues, they are all separate, then we will have a unique set of x star, y star, z star, which obviously are mutually perpendicular. If two of the eigenvalues are equal and not equal to the third one, then what happens? Then what can we say about the eigenvector in the 1, 2 or xy plane? If I11 and I22 are equal and I33 is something totally different, then any vector in the 1, 2 plane is what? It is an eigenvector. If I11 is equal to I22 and not equal to I33, probably you will recollect this once you hear this, then any vector in the 1, 2 plane is an eigenvector. Okay, this I am not proving, you refer to your maths. What am I saying? I am saying if two of the eigenvalues are equal, so now I33, there will be a vector corresponding to this, so that will form, now perpendicular to that vector there will be a plane, that will be the 1, 2 plane. Now any vector in the 1, 2 plane will be an eigenvector. So therefore we can choose any two mutually perpendicular vectors in the 1, 2 plane, and 3 is always anyway perpendicular, so then 1, 2, 3 will form the eigenvectors and they will be principal axis. So therefore there can be more than one principal axis. I have answered your question. You asked that, so there can be, but it will be in this special case. In this special case, if I1, so now let's write this again. So first of all what we have shown is, if this is there, then first of all V3 vector, let us call that as Z star. So this is an eigenvector. Perpendicular to Z star we will have the 1, 2 plane, and any vector in the 1, 2 plane is an eigenvector. So what this implies is, if any vector in the 1, 2 plane is an eigenvector, that means x star, y star are any two mutually perpendicular axes in the 1, 2 plane. So therefore now the uniqueness has been taken away. It could be anything in this 1, 2 plane. Is that clear? I am trying to make it as physical as possible, and probably you are trying to get some physical meaning to the maths which you have studied in your maths course. Okay, there is one case we have not discussed. What is the third case? If all three are equal, then what will happen? Then any three axes will be the eigenvectors. Pardon? Sphere. Sphere is an example, and I will come to that. So now if let's move on to this. So let me just so if I11 is equal to I22 is equal to I33, this implies any vector is an eigenvector, and so choose any three x, y, z which are mutually perpendicular. Is that fine? Now keep this in mind. Let me then tell you a way in which we find the principal axis by symmetry, and then I come back to these arguments which will show some very interesting things which are not very obvious. Okay. So now given this, so this is that's the only maths or only thing related to eigenvectors which I wanted to do, and I will not be asking you to calculate these things on the basis of eigenvectors. I will not ask you in this course to calculate any eigenvalues or eigenvectors. I can do that, it's also simple, but I think that's just a small algorithm. There's no, if we need to do it, we can always You go to the computer, use MATLAB, find eigenvalues and eigenvectors. It's the easiest thing to do rather than doing it manually. Why should I do it manually? Okay. So now, what I tell you is, let's try to see how do we locate principal axes by inspection. And this is what I had done last time, but probably in a bit of a hurry, and this is what we should be able to do. Locating principal axes by inspection, and this we will use. Firstly, we will use the argument of symmetry, and maybe the arguments used earlier in the class to determine something more. Now, what symmetry tells me is, suppose if we have a plane of symmetry in the body. Let me first write down the conjecture. If there is a plane of symmetry in the body, then the axis perpendicular to this plane of symmetry is a principal axis. If there is a plane of symmetry, perpendicular axis is perpendicular to this plane, and let us show it by an example. Suppose I have an ellipsoid, and if I mark my axis on the ellipsoid like this, sometimes I'm using all sorts of this thing. Sometimes I'm using x coming out, sometimes x going, z going up, or whatever. So sometimes this is x, sometimes this is x. It doesn't matter. Now here, let us try to identify. In fact, the way I have made these axes, any plane passing through the center is a symmetric plane, is a plane of symmetry. Okay. If I look at, let us look at the xy plane. XY plane is which plane? The horizontal plane. So XY plane is a plane of symmetry here. So let's start, let's look at this. So let's try to explain. XY is a plane of symmetry. It divides the body into two parts, top and bottom. Now what does my conjecture say? My conjecture says if xy is a plane of symmetry, then z axis, which is perpendicular to the xy plane, is a principal axis. So now if I look at Izx, this will be equal to integral x times z times dm. Now for each, I can divide this into two parts, integral xz for top dm plus integral xz for bottom dm. Now since xy is a plane of symmetry, for each x which is common, there is a z and a minus z. At the top part, wherever the z takes the value z, for the same x, the bottom part will take the value minus z. So when I add the two, what do I get? 0. And when I add it up over the entire body, what will I get? 0. So that means Ixz will be 0. Similarly, when I look at Iyz, I will get the same thing. For every z, I will have, or for every y location, I will have a z and a minus z, which will be the same, and z, because it takes opposite signs with algebraic signs for the same y, when I sum it up, I will get it as 0. So when I divide it into top and bottom like this, I get z is a principal axis. So Ixz or Izx is equal to 0. Similarly, I look at Izy, this will be equal to integral yz dm, this will be equal to integral on the top part yz dm plus integral on the bottom part yz dm. This will be 0, as for each y we have a z and a minus z. Okay. So, in this case, when I look at this body, I get x y was a plane of symmetry. Now, y z is also a plane of symmetry. That means x is a principal axis. If x is a principal axis, what is 0? I x z and I x y. So, therefore, all the three axes are principal. But also you note, suppose had I put this axis somewhere here, I have put them at the center, even if it was displaced from the center, still x y and y z would be planes of symmetry. And if that is so, then x y z axis would be symmetry, would be principal, even though x z is not a plane of symmetry if the axes are shifted, but still x y z are principal axis. Does everybody see that? And so what we have shown is that symmetry tells us that there is a principal axis, but principal axis does not imply symmetry. It could or could not be, but symmetry means any axis perpendicular to that is a principal axis. Is that clear? So, this is, and this way we can locate, if we find two mutually perpendicular planes of symmetry, then the axes which are formed by the intersection of these two planes, they will be principal, irrespective of the third axis not being perpendicular to a plane of symmetry. So, if there are two mutually perpendicular planes of symmetry in a body, then the axes which are formed by the intersection of these two planes, they will be principal axis. Okay. This is what I was referring to last time, maybe I had not done it very clearly. So, for example, I can probably get to that. So, example 2, even if I have a body like this, now in this x y is a plane of symmetry, this implies z is a principal axis, and y z is a plane of symmetry, and this will imply x is a principal axis. And these two things will imply y is also a principal axis even though x z is not a plane of symmetry. Okay. Has this clear? So, this is how we work out locating principal axis by symmetry. So, then let me, symmetry implies perpendicular axis is principal. Principal axis may or may not have the perpendicular plane as a symmetry plane. So, principal axis does not imply that plane perpendicular to it is plane of, it may or may not be true. ठीक है. Now let me just repeat a simple formula we had done last time. Just absorb this, and then as I told you, this has some nice connotations with regards to some bodies which now we'll be able to explain. So maybe I can just first come to first let me do the formula once, and then I will do this thing. Okay. So now we had done two theorems last time. One was the parallel axis theorem. I will not do that again today. Parallel axis theorem is, if we know inertia matrix at one point and we want to shift it to another point, we choose a set of axes which are parallel, and then we use we find the inertia matrix at the centroidal point. Even if we don't know, then we go from point A to the centroid, and from centroid to point B, and we find the moment of inertia of parallel axis. The second theorem we did was that if the origin is the same and we have an axis which is rotated with respect to the initial axis, then how do we find this thing. So let me just go, I didn't derive that, let me just again probably go through the bit of this thing. I will not derive it, but we know. So rotation theorem is used if we know the inertia matrix. Now for using the rotation theorem, actually we need to know the full inertia matrix. If we know the inertia matrix with respect to x, y, z axis at a point A, and we wish to find I k k or I k of an axis k which passes through A. So let us draw a cartoon. However, we have a point A, we have x, y, z axis at A, and then we have an axis which I call as the KK axis. Now, if I choose any mass dm which is located at a vector r, so that means this vector is r. Let lambda be the unit vector along KK. So unit vector along this is equal to K. Now if I drop a perpendicular from here and let this distance be d, then dm multiplied by d square integrated over the entire body will give me ik. Okay. So ik will be equal to integral d square dm. Now this vector is r, unit vector along this is lambda. What is the distance d? Distance d, if I write this angle, if this angle is theta, then d square will be equal to r square sin square theta, and this I can write it as lambda is a unit vector, r is the vector along r. So, when I take lambda cross r, the magnitude of that will be what? R sin theta. So, lambda cross r square is what will give me d square. So, that means what I have to do if I have to find I k is equal to integral of lambda cross r square dm. So, that is what I will have to do. Now, lambda I can write it as lambda x, lambda y, lambda z, the three components, or it can be, we can use the three components of lambda in terms of I, j and k will be nothing but its direction cosines. Okay? That is the simple maths. The direction cosines of lambda will be LMN, or I can write it in your book notation as lambda x, lambda y, lambda z. What is the coordinate r? What is the vector r? Vector r is nothing but x, y, z. So, all I have to do is I have to find I, j, k, lambda x, lambda y, lambda z, x, y, z. I have to find this vector and take a dot product of this vector with itself, because I have to find the magnitude square. So, that means what type of terms I will get? I am not doing the derivation. I will get lambda y times z minus y times lambda z, and I have to take a square of this. So, when I take a square, I will get lambda y square z square. I will get lambda z square y square minus 2 times lambda y lambda z y z, and so on. So, I will get terms like this, and then what I will do is I will club all the terms together. I will take all the lambda x square common, and then whatever comes, and what I will find is with lambda x square I will get y square plus z square. With lambda y I will get x square plus z square, with lambda z I will get x square plus y square, and then I will get some products. And when you take all these integral, all the integrals will be in the form of ixx, ixy, xz, or the products of inertia. The products of inertia will come from lambda y, lambda z, yz term. Lambda y, lambda z can be taken out of the integral. Integral yz dm will give me iyz, and so on. So, basically, once you expand this, let us not go through that. I think all of you can do that. You go at home, you do it, you should be able to do it. Then the final form what we get, and this is what I wrote in the last class. Once you go through this, what we got was I about the k axis is equal to lambda x square ix plus lambda y square iy plus lambda z square iz. Then I get minus 2 lambda x lambda y ixy minus 2 lambda x lambda z ixz. So, this is the formula which comes like this. I had just given you this formula without giving any basis of this in the last class, but I thought at least you should know how it comes. So, this is just coordinate transformation. This is how one can get ik. Okay. Now, similar to this, there is one more formula which I think I will just write without even giving you the motivation, and that is not used in our text. Suppose if there is another axis q here which is perpendicular to k, then the product of inertia iq I can find by the same formula. Instead of k I will put q, but I can also define something called ikq, because k and q are mutually perpendicular. So, there will be a transformation formula for ikq also, which can be worked out, and that I will just write it. I will not, I think that is why I will use even a red pen for this. So, if the q axis has direction cosines L prime, M prime, N prime, and k axis has L, M, N, then ikq will be given by minus L L prime I x minus M M prime I y N N prime I z plus L M prime plus M L prime I x y plus, you do not even need to write this, it just will be there. I will x z plus M n prime plus N M prime y y z. So, this is just a transformation formula for product of inertia, which I do not think we will be using in the course. Just doing it for the sake of completeness and probably to show one or two beautiful things which we will otherwise show from maths and the eigenvector concept. So, now before I move on to some calculations of moments of inertia, let us see the thing which I was talking of. And okay. So, now this formula anyway it will be there, I will put these notes, they will be available to you if I have not taken down, you do not need to. And also I have told you for exams you do not need to remember, all the transformation and these formulas will be provided to you. Of course, you should know the meaning of the symbols, what is L, M, N and so on. But is there some relation here? When deriving these formulas, certain things are used, and two of the things which we use are, what is the relation between L, M and N? Is there a relation? L square plus M square plus N square is equal to 1. And between L, L prime, M, M prime, N, N prime, is there any relation? L, L prime plus M, M prime plus N, N prime is equal to 0, because they are mutually perpendicular. So, these relations are there, and obviously L prime square plus M prime square plus N prime square is also equal to 1, because they are direction cosine. So, these things we should keep in mind. Now, what I was saying, and when I was talking about symmetry, you rightly pointed out, the most sort of symmetrical object in terms of three-dimensional thing is what? A sphere. Now, if we look at, let us look at a sphere, and let us place, so we have a sphere, that means this is a three-dimensional object, not a cylinder, and if I place x, y, z like this at the center. Now, clearly any plane is a plane of symmetry, not only these x, y, z, any x, y, z I choose is a plane of symmetry, and also from symmetry you know whatever is I x is equal to I y is equal to I z, and they should be the same for any axis. Okay. So, now here for sphere what we know is from symmetry, let us look at this one. I x is equal to I y is equal to I z, that is the first thing which we go, and then we also know from symmetry that I x y okay. Now, given these two facts, now for a sphere it is very obvious, we know these two facts are there, but also we know any vector which if I choose x, y, z in any other way, as long as they pass through the origin, the same results will be valid because of the symmetry of the figure. And if we try to verify these things from the formula, suppose we look at it, let us try to see. I choose an axis k, which is some arbitrary lambda x, lambda y, lambda z. What will I get? I about k is equal to lambda x square I x plus lambda y square I y plus lambda z square I z plus 0. Now, I x, I y, I z are all equal. So, then it will be lambda x square plus lambda y square plus lambda z square times I x, which is 1 time. That means any axis I get the same moment of inertia. Is that clear? Does everybody see that? So, it had to follow obviously. Now, what about product of inertia? Let us try to see. When I try to choose any two other axes which are mutually perpendicular and try to use this formula for product of inertia. Now, L M N, L prime, M prime, N prime can be anything, but because they are mutually perpendicular, L prime plus M prime plus N prime is equal to 0. So, now if I use this formula for any k q, I will get minus L prime I x minus m prime iy minus n prime iz plus 0 with respect to these axes. And because these three are equal, we will get minus of l prime plus m prime plus n prime times ix, which must be equal to 0. So, any two mutually perpendicular axes, we get a 0 product of inertia. Is that fine? So, if this also is a very simple example, if I know original products of inertia and moments of inertia, I know the inertia matrix about x, y, z, how to find it about x prime, y prime, z prime. I do not think this is too tricky, but now let us try to look at this case. Let us try to look at a cube. And if I place x, y, z axis at the center. So, origin of x, y, z axis are at the center and x, y, z are parallel to the cube edges. Now, one thing I will do without proving here is Ix, Iy and Iz. If I choose these three axes, obviously I have chosen a special set of axes. Now, this object is not symmetrical like a sphere. Okay, I have chosen special axes. Now, about these axes, obviously Ix, Iy, Iz have to be the same because they are mutually perpendicular to the parallel edges, and this is equal to, if this is made of a regular material, which obviously it has to be if we are talking of symmetry, then it is given as ma square by 6, where a is the length of an edge. Okay, this is about the center. Now, what can I say about planes of symmetry? Now, we are starting with this object. We have chosen one axis. I do not know the products of inertia as of now. Now, let me try to deduce what the products of inertia are. Is x, y a plane of symmetry? So, that means z is a principal axis. Is x, z a plane of symmetry? Yes. So, y is a principal axis. So, from symmetry it is obvious here that these x, y, z are all principal axes. So, I start from this, I start given these things are given to me. Then I deduce from symmetry x, y, z are principal axes. This implies I x y is equal to I y z is equal to 0 for this axis. For these coordinate axes, these are 0. Now, let us go to our original argument, where we said if we have a set of principal axes and if the three eigenvalues are equal, what deduction did we have there? Any vector is an eigenvector. That means what I am saying here is, and if any vector is an eigenvector, the eigenvalue corresponding to that will be the same again. I11, I22, I33, they are all equal. So, what I am saying here is, if I go about any arbitrary axis, I will still have the moment of inertia about that axis will be ma square by 6, which is not obvious from symmetry. From symmetry I can't say, and also it says that any axis is a principal axis. Now, obviously there is no symmetry about some axis passing through this at some arbitrary angle, but what my eigenvector argument tells me is any vector is an eigenvector. That means any axis is a principal axis and the corresponding eigenvalue is the same I11, I22, I33, ma square by 6. Is that true? Let us verify that using the formula. So, now let us show for any arbitrary I k, I choose some k. So, I do not know its direction cosines, all I know is L square plus M square plus N square is 1. So, then let us see lambda x square I x plus lambda y square Iy plus lambda z square Iz, remaining terms are all 0. So, for that arbitrary k axis, what do I get? Ik is equal to Ix or Iy or Iz, and which is equal to ma square by 6. And if I look at this Ik cube, once again I will get that will be 0. So, for Ik, if I look at any q axis, that means k will be a principal axis also. So from here, what mathematics told us collaborates from the formulas, and we are able to show that whatever axis we choose, as long as if the 3 eigenvalues are equal, and if they happen to be the three moments of inertia are equal and they are principal axis, then any axis passing through this will give us the same value of moment of inertia. I don't need to calculate them by using complex integrals. If I can establish this, all I can do is use this, and that is my answer. And similar thing will happen for planar things. If I11 is equal to I22 and not equal to I33, then anything in the 1-2 plane will be the eigenvector, and I11 is equal to I22 will be equal to the moment of inertia of any axis in that plane, about that plane. So, this is how we can get these results. We can sort of see how mathematics already told us these things. Just by saying it's an eigenvector, we've got this, but then the formulas do tell us, and the proof comes from the formula. Is that fine? So, this is what we have for now. How do we find moments of inertia? Now, this is from your textbook directly, that if we have a homogeneous body, then the moments of inertia are found by, we have about an axis we have to find. So, it is r square dm. If it is homogeneous, then we will write it as rho dv. Rho can be pulled out because it is a homogeneous body. Now, this dv, we can either write it as a dx if we can break the body into different slabs. And when we have two planes of symmetry, then we choose thin slabs perpendicular to the plane of symmetry. If there are two mutually perpendicular axes, perpendicular planes which are symmetric, then we choose thin slabs perpendicular to this body, and for each of these simple bodies we may be knowing the moment of inertia, and then we can integrate that to work out the moment of inertia for the total body. Now, you may have done, let us see before we do this. So, for example, I have already said this, I do not think I will complete the argument, you must have followed that. So, now let us see. So, if we have a thin body, how do we find the moment of inertia of a thin body? That means we have the body is in the xy plane and the z dimension is almost 0. Now, here Ix will be equal to integral y square plus z square dm, Iy is equal to integral x square plus z square dm, and Iz, which is perpendicular to the thin plane, this will be x square plus y square dm. And this leads to what you know in your school as the perpendicular axis theorem. If you put z going to 0, what do you get? Ix is equal to integral y square dm, Iy is equal to integral x square dm, and Iz is equal to Ix plus Iy. So, this is what leads to what is termed as the perpendicular axis theorem. So, perpendicular axis theorem is valid for thin bodies. So, now here we have this will go to 0, this will go to 0. So, we have Ix plus Iy, and this is what textbooks, at least in high school physics books, you read the perpendicular axis theorem. and this is what one can use when you have thin slabs. Each of the slab will be like this. Now, you have done, see for example, if you want to find the moment of inertia of a ring or of a, now if we have a disc, a thin disc, we want to find its moment of inertia, then we choose, so this is x, this is y. Now here as I said, sometimes I will change, z is the one which is coming out of the board. Now Iz is equal to x square plus y square dm. So if this is a point where your dm is, so this one can write it as r square dm. Okay, and now you can work out dm. So that means you can basically choose a small ring here, all this at a distance r, this total radius may be r, and then when you work this out you can show Iz is equal to mr square by 2. Okay, because dm will be nothing but 2 pi r dr. So this you put it as 2 pi r dr multiplied by rho, and then you have r cube dr, that will give you r4 by 4, and then put rho as capital M by pi r square, you get this. Now from here also you know x and y are symmetry axes, so therefore Ix and Iy they have to be equal, and they will be, sum of that must be equal to this, so therefore Ix is equal to Iy is equal to mr square by 4. Okay, so you use symmetry arguments and things like this to basically get things for very simple bodies. If it's a complex body, then we use integration. So that is what I'll probably, let's look at this. So let's now try to find some things for some simple bodies. There's one which is not given. If we have a cylinder x, y, z, and this is at the center, let the length of the cylinder be L. Then first of all, Iz for the cylinder passing to the centroid, this is equal to mr square by 2, and Ix, the bar sign represents that this is at the center of mass. So Iz bar is equal to I by, this is equal to m by 12 3r square plus L square. Again this formula can be derived by taking small slabs, each ring you know its Ix, Iy, Iz, and then you can integrate that to get this. Okay, so this is how one gets Ix bar plus and Iy bar will be equal to this for the cylinder. Now from the cylinder, two simple cases come. If the length goes to 0, we get the disk, and we put L is equal to 0, you get mr square by 2 and mr square by 4. A second very important case which comes is what we call a slender rod. This will be very often, it will be used in the course, slender rod. Attendance sheet aa gayi kya? Where is it? आज मैं सोच रहा हूँ थोड़ा चेक किया जाए प्रॉक्सी वगैरह. Today would be a good day. Let me see. Okay, let me first finish this, then I will check all this. अगर किसी ने प्रॉक्सी लगाई तो पहले ही हटा दो, काट दो. आके यहाँ पे काट देना अपने दोस्तों की, नहीं तो your friends are in trouble जिनकी प्रॉक्सी लगी हुई है. Okay. So अभी फोन करके बुला लो उनको before I check. So now if we have a slender, okay, we have a slender cylinder. For a slender, what we will have is, what will happen here? R goes to 0. So what will be Iz? It will be 0, and Ix is equal to I bar, Iy is equal to ml square by 12. Okay. So for a body like this we get. So Here I have taken this from the book. So, this is for a wire or for a slender, the first one, I y is equal to, now here x is taken as the axis. So, what I wrote earlier, I wrote z as the axis. So, there he is getting I y is equal to I z is equal to 1 by 12 ml square, and what he forgot to write here is I x is equal to 0, and obviously all are principal axis. See, when we have regular bodies, we will have principal axis. Now, this is a thin rectangular bar along the x direction, its dimension is not given, that will be a. Along y, the length is b, along z, the length is c. Yeah, that's right, a, b, c. So, now I x, which is this one, see what here the formula goes like this, 1 by 12 mass times square of 2 lengths, and the 1, if you are looking at the x axis, that dimension will not count. So, therefore, along I x means y square plus z square, along y the dimension is b, along z the dimension is c. So, b square plus c square, but these 1 by 12 formulas are for the center, not for the edge. Similarly, I y will be equal to 1 by 12 m times z square plus x square. So, the dimension along z is c, dimension along x is 0 here. So, therefore, it will be 0, otherwise it will be plus a square. If the dimension along x was a, then it would be c square plus a square, and similarly I z 1 by 12 m b square. And the general formula, as I said, this is given here for the parallelepiped a b c. Okay. Now, then here of course, okay, here comes the formula which I was talking of, the formula for the cylinder, which I have already written to on the board, for the disc which follows from this by putting z is equal to 0. For a cone, you can still, these things could be worked out. I x turns out to be 3 by 10 m a square, I y and I z are given by this. Maybe this you can derive. You take a thin slab, each disc, but now as you integrate with z, the radius of the disc changes, that's it. So, then this formula will follow. And for a sphere, it is equal to 2 by 5 m a square. So, this again can be shown. Basically, it is a simple, it will become a hemispherical shell, which is there, whose mass will be 4 pi r square dr. And when you integrate that, you will be able to get it. So, this is for each hemispherical shell you keep on integrating. So, you will get. See, what you do is you do it as I x plus I y plus I z, that will be equal to 2 times I x plus I y plus I z will be 2 times x square plus 2 y square plus 2 z square. So, 2 times moment of inertia will be equal to this, and then you can get it very easily. So, these formulas will all come. Now, what comes from all this then? After you do this, the problem which could come, and that is where I would like to be the last example for today, which is slightly involved, but I was told that the classes are getting a bit boring. So, you keep only examples for the end. So, that is what I am doing today. Let us say we have a disc of radius r and mass m1. So, this radius is r and mass is m1, and this is mounted on a light shaft of length L. So, this length is L, and this is mounted on this. This angle here is given as theta. The angle shaft makes an angle theta with another vertical shaft. Now, the vertical shaft, the vertical axis is z. The question is, find Iz of the shaft and disk assembly so this is the shaft and this is the disk. We have to find I about Z, that means about this vertical axis of this disk. How will we do this? So now what do we know? Let's start with it. Obviously we know about shaft is light, so its moment of inertia will be 0. No contribution from the light shaft, only contribution will come from the disk. So half out of 10 if you talk in terms of marks in the minor. Okay. So now we have to find IZZ of this disk about the Z axis. What we can do is, let us form, so let us say this disk we form at the disk center of mass. I put in centroidal axis x, y and z is coming out of the board. So I put centroidal axis, I put place x prime, y prime, z prime axis on center of gravity of disk. Okay. Now why do I choose x prime, y prime, z prime as these inclined axes? Because for these inclined axes I know products of inertia will be what? 0. I x prime, y prime, I y prime, z prime, all these will be 0 because these are symmetry, these are axes of symmetry. Is that clear? So now what I will first do is, let me find, so now let's, where is the z axis here? The z axis, parallel z axis, let me show it by red color. This is the z parallel which is passing through the center. So now z bar axis is parallel to z passing through center of gravity. So first thing what I will find will be I about the z bar axis. I will find the moment of inertia of this disk about the vertical axis passing through its center of gravity. What do I need for that? I will need, firstly, so I need the initial moments of inertia and I need the direction cosines. So to work out this problem, let's see, the easiest way we should just follow an algorithmic approach. So what I am doing is, I know x prime, y prime, z prime axis, inertia is known and we wish to find about z prime axis. So first of all let's write the direction cosines of the z prime axis. Now this is the z prime axis which is the vertical axis. What is the angle between z prime and x prime? This z axis which is passing through center, not z prime, sorry, the z axis and x prime. What is the direction cosine between these? Cos theta. The angle made is theta, so the direction cosine is with x axis is cos theta. What about what the angle which this vertical axis made with the y prime? It is 90 plus theta. So therefore its direction cosine will be minus sin theta. It's an obtuse angle, and if this is cos theta, the other one in the same plane has to be sin theta, but because that's an obtuse angle, it will be minus sin theta. How is it obtuse? If this angle is acute, what will be the other angle? 90 minus y. Let's see. See, look at the y axis that's going that way up, and this angle. So what's the angle between? So that is that axis, this angle. It will depend on how you are looking at at y prime, it's going upwards or downwards, or z prime, okay, is z prime going upwards, okay, so then it will be just sin theta, okay. So if z prime is going upwards, I was looking at it downwards, so it doesn't matter, as you will see. So the direction cosines is, with x axis it makes cos theta, with y prime it makes cosine of 90 minus theta, so it will be sin theta. See, this is the angle, okay, so what you are saying is it will be minus, okay. So if let's say, okay, this, if you are taking it, I was taking it as going, it should be taken as going up, the angle which this makes, okay, so this will be minus cos theta sin theta if z goes up, and it will be cos theta sin theta 0 if z goes down, okay. Now let us write what are I x prime, what is I about x prime, this will be m r square by 2, m1 r square by 2, I y prime is equal to m1 r square by 4, and I about z prime is equal to m1 r square by 4, okay. And these are principal axes. Now all I have to do, see, in these problems for rotation thing, these two things have to be done, and all the products of inertias are 0. So all now I have to do is apply the formula. So now if I go to the formula which I have just derived here, ik will be equal to cos square theta ixx plus, and that is why plus or minus will not make a difference, plus sin square theta m r square by 4 and m r square plus 0, lambda z is 0, everything else is 0. See, the formula is very big, but when you typically apply it, it will become, you will only have the first 3 terms, and maybe one of them is also 0. So therefore when you apply this formula, what you get is, it's as, so once you have written this, then the formula application becomes quite straightforward, and what we get is, so therefore I about z prime, this becomes equal to m1 r square by 2 cos square theta plus m1 r square by 4 sin square theta. This is about z prime centroidal. Now we have to find I about z. So this is the z axis, this is the z parallel axis. What is the distance between these two axes? The perpendicular distance between these two, L sin theta. So that means I about z will be equal to I about the centroidal z plus m times L square sin theta, L square sin square theta. So now the perpendicular distance, this will be equal to I z bar plus m times d square, where d is the perpendicular distance between z and z passing through C, and this perpendicular distance is equal to L sin theta. So I about z will be equal to I z bar plus m1 times L square sin square theta. So this way we use both parallel and perpendicular axis theorem, or parallel axis and rotation theorem, to find out this thing. Is that clear? So this is an example of trying to find out.